Or listen my voice. I think I'm audible. If any network issue from my side, any screen sharing issue or any audio issue, please let me know. Okay. While sharing my screen, please give me 1 minute. Yeah. First of all, I want to introduce myself. I'm Meenakshi and I am working as an design verification engineer in AMD, and I have done DDR4. I have some involvement and I developed some test cases. And what are the things we have to do in DDR and the basic protocol knowledge, industry level, what they want. Those are all the things I want to deliver in these couple of weeks. First of all, I need to start with what is DDR. Why DDR? Why DDR is that much demandable in present industry? If a person who have shortlisted their resume because of the demand of the DDR protocol also. So I think this is a very good opportunity to take all these things, which you have a better future in upcoming industries. Okay, I'm starting my session. If you have any doubts, please let me know. I hope, can anyone please confirm my audio and video screen sharing is properly occurring?
Yes.
Yeah,
ज्वाइन करके देख रहा हूँ
thank
मतलब लिंक आ गया था सुबह पर अभी मैसेज नहीं आया कि ज्वाइन करो ऐसे
Sorry, can you speak in English? I don't have. Hello, hello, hello. Right now, someone talked. I didn't get you actually. Can you speak it once? Or else anyone? Please confirm. I need to start the session.
Yes, it's audible and screen was visible.
Yeah, thank you. Thank you, Shrikant. If you have any doubts, please let me know. Can stop wherever we are in discussion. Please let me know. Yeah. So what is DDR? Why DDR? These are the main things first we need to know. So DDR comes under memory session. Means memory is nothing but we need to store some amount of data. Here we have different types of memories we have. That is some semiconductor memories. Actually, we know what is memory, types of memory. Memory is nothing but storing some data, RAM memory, ROM memory, generally things. But in depth, we have different types of memories. Like what? We have some sequential memories, that is LIFOs and FIFOs, last in first out, and some random memories. These RAM and ROM are comes under random memories. That is nothing but random access memory, random comes under temporary memory and permanent memory. And the main difference is between the RAM and ROM is the whether the data should be stored in a temporary or the data should be stored in a permanent way. Here, RAM means when volatile means nothing but whenever, for example, we are doing some project, some changes we are doing without saving, suddenly my laptop was shut down. So the data which I didn't save, those the data is completely erased. That is nothing but volatile memory. Means when the remaining what the thing I worked that already saved is stored in the secondary memory. That is nothing but the permanent memory. So these RAM comes under SRAM, DRAM. These all are comes under temporary memory. Means that nothing but these all are comes under volatile memories only. And these DDR DDR, DRAM, SDR, DRAM, these all are comes under volatile memories. And coming to the ROM, there are some programmable memories, E square PROM, EPROM, and some flash memories. All this comes under non-volatile, and some cache memories and SRAM memories. All this comes under volatile memories. And coming to the SRAM and DRAM, what is the main difference between the SRAM and DRAM? Why DRAM is only used in DDR project? What was the main advantage to use DRAM? For that, first of all, we have to know what is SRAM. SRAM is nothing but static memory. Means here we are having generally for to develop SRAM, we need to how it need a minimum 6 transistors. Here these are cross-coupled inverters. Means in cross-coupled inverters also we have 2 transistors. So one transistor plus two, three, three, 3 plus 1, 4, 4 plus 2, 6. Total 6 transistors we need for to develop one static RAM and to store only one bit of information. And there is no and also we have some word line and bit line, and there is no refresh is required in SRAM, even though for to just storing it main cause of the transistors. For example, in future we need to store some big amount of data, for example 1024 bytes of data. So for that we need to develop some 2 power so on, so 34 64, those type of bits we need to store. So it is more complexity to develop these using SRAM to build only one to store only one bit of information. But it compared to the speed, it is more speed compared to DRAM, but the storing is increased, so complexity increase. So these all are the after increasing the complexity, the development is increased, verification takes so more time. So these all are the drawbacks we have in SRAM. So those all the drawbacks we are removed in the DRAM. Coming to the DRAM, in DRAM, we just need only one transistor and one capacitor here to store one bit of information. And as I mentioned previous, they are word line and bit line, where the word line is nothing but here the address line. Whenever we get the power supply, VDD supply or 5 volt supply uh, uh, from our system power clock, then immediately the transistor comes into the circuit. Whenever the transistor is on, then the electron flow is occurring from the transistor to the in the capacitor level. Then the bit line should be activated. Then excuse then the data should started storing in this capacitor. Capacitor is nothing but to store the data. uh, for what it need to store up to the threshold voltage. Every capacitor should have some threshold voltage value. Up to that it can store the data. After the storage, the threshold voltage 3, for example in these capacitor threshold voltage is some volt, some 3 volt for example. Yeah, after up to 0 to 3 volt it started storing the data. Then after 3 volts it need to be discharge the data. So for these discharging, we need to what are the data previously we stored, we have to protect our data. So without discharging, we have user come this refresh operation comes into the picture. Then where after 3 volts, then the refresh should be occurred continuously. Means there is no discharging is we are not giving any space to the discharging, we are just storing the data. So this refresh command is mainly targeted in the DRAM. In SRAM we didn't use any refresh is required. See here, no periodic refresh is required because we are using just transistors, no capacitor. But in DRAM we are using And coming to the DRAM, so initially the main difference of the DDR, main why it came into the picture. So initially we are trans transmitting the data at one edge, either it is in comes under passage or negate. For example, we'll wrote always at the rate of passage of clock or always at the rate of negate of clock. Every changes occurred in the clock cycle, the data transition should be occurred. But coming to the DDR, DDR means a double data rate. Every clock edge either comes, the data should be transmitted passage of clock and the negate of clock. In two edges we are transmitting. So for that, the more clock cycles is not yet required for to transmit our data. So initially DRAM we have, then comes SDRAM, then DDR 1, 2, 3, 4, and 5 also done. And right now we are working on DDR6 present. Uh, and coming to the DRAM architecture here, some asynchronous DRAM architecture. DRAM architecture first to store one bit of information, how the process internal architecture, how it going on. See here, we have in mainly memory, how DRAM memory will store. It comes under like row axis, two dimensional arrays or three dimensional arrays, how we have, like that the memory storage should be happen. Means you need to select some particular row and we need to select some particular column. At that particular point only we need to store or we need to retrieve the data. See here, DRAM architecture, we have some row addresses. So what are the uh, data I need to access, or I need to access that particular row. So those data should be converted. Here we are using so many converters. Our AXI data should be converted into our DRAM data. Then our row decoder is there. In this array, we need to select that particular column or particular. Sorry, we need to select here particular row. For example, here we are having 0 to 32 rows. Wait a moment. Minute. See, for example, here we are having 0 to some 32 only we are considering. So after row decoder, we are getting the row value as 17. So the 17th total row value, total row, how many columns we don't know here. We just ignore that columns right now. The 17th total row should the data, what are the data present in the 17th row, should take it into the sense amplifiers. See, this is called the sense amplifier. What the sense amplifier will do means, it, what are the data we are selecting that particular row, the data should be taken into that sense amplifier. After that, the column decoder comes into picture. Then after some clock cycle, TRCD delay after, we need to select our column. So 17th row we are taking into these sense amplifiers. Then after column decoder, in 17th row, we need the data present in the fifth column. So the particular data should be taken. Either we need to perform the read operation, we need to perform the write operation. So that particular row we are writing into the data. So these are the internal things should be occurred while selecting the row address and column address. After selection of the row address, we need to select the column address. After selecting the column address, we need to do whether we need to perform the write operation or read operation based on the how many clock cycles should be required for to complete the big amount of data we are calculating using DRAM addressings. So up to this, do you have any doubts? Please let me know, or else I will continue this presentation. See here some important points. Asynchronous DRAM architecture means why it comes into the main DRAM architecture only comes into the picture. This is the independent timings, variable timing, separate control signals, a simple interface,
Huh?
power consumption. Yeah, yeah.
Your voice is breaking. Sometimes it's coming like low and sometimes high.
Sorry, my actually my network is very good. Can you please check it from your side? Only for you or everyone also? Can anyone please confirm?
For me too, madam. Sometimes it goes high, sometimes it's low.
Okay, maybe network issue. Okay, I will solve from my side. So please check my pitch. Is this pitch is sufficient? Hello?
Yes, madam.
Yeah, yeah. Okay, whenever I am low, please let me know. Actually, okay, at that point, please let me know. Whenever I am low. Whenever I am lowering my pitch. Okay, these are the smaller things you need to just get an idea. So coming to the SDRAM architecture, right now we are done with the asynchronous DRAM architecture. Coming to the synchronous DRAM architecture. So how the internal architecture will have. See, as now I discussed the row address decoder, column address decoder. So the same, but we have some synchronously we need to do here. See here we are having some mode registers and control registers and some other ODT registers and some other BCW registers. All many registers we have. So for that, this is RAS is nothing but row address select. So first we need to, after the clock enable should occur, we need to select the chip. Which the type of chip we are operating. Which chip selection we are doing. And after chip selection, we need to select the rows, banks, bank addresses, ranks, all the things. Whether we'll go depth, you'll get some other clarity. So after selecting the chip, we need to select the row address using row address decoder. After selection of the row, we need to select the column address decoder. After column address decoder, we need to give whether we need to perform read operation or write operation. And meanwhile, we are having some refresh timers. After completion of the particular time, we need to do refreshing. For example, I think zero point 0.4 microseconds after we need to do every refresh command should be occurred. It is an automation refresh command we are using. For every particular, we need to set that refresh automation command. After particular zero point 0.8 microseconds, every time we need to refresh the data. After that, uh, we need to do perform multiple operation. Meanwhile, we need to pre-charge the commands, all the things. But in go depth, you have some clarity. These are the basic things. See here, right now we are done with the industry level. We are done with the DDR5. Does anyone have working idea related to DDR5? How the industry is occurring? Did anyone work related DDR subsystems or any blocks related to DDR? Okay. Actually, DDR6 is working. DDR4, 5 is done. Mainly, okay, well, if you want to, I want to give some insights from DDR from my experience. You need to learn through total protocol. First, you need to follow the JDEC spec. You have to, I will, okay, after, I will ping you in chat box. I think it may helpful to you later. You need to download that JDEC spec. After downloading, you need to just have a look on it, all the spec, how it going on, what are the things. Then you need to focus on which how to work on it, either 3 or 4 or 5. I preferred 4 because 5 is done recently, 6 is working, 3 is also fine, but 4 is upgrade version in industry. So I think 4 is better to you. So, and if you want to learn more DDR in depth, you just want to read that spec. After that, develop faster DRAM. DUT development is more difficult VAP getting. So generally, we are using Cadence VAP. VAP we are taking from the Cadence only. We are just verifying that whether what are the upgradations done in 4 is working or not, like that. So coming to this session, DDR1 to what are the differences? DDR is mainly, I mentioned that mainly it is used for the rising both clock edges, either rising and falling edges of the clock data should be transferred, and the data transfer should come is more speed compared to the previous one, like SRAMs. Previously we are used so many other things, so compare all that, DDR is more efficiency and it is very speed also. And DDR transfers rate 266 to 400 mega transfer per second, means it works under 800 megahertz per clock cycle. So every within second mega transfer second means in 1 second we need to transfer 400 data with some. So it comes under 2N prefetch architecture. Prefetch architecture, what means I will give let in depth. And these DDR mainly works under the these chip selection, rank selection, banks, bank groups, row address, row selection, column selection. How the internal architecture will have idea whether we'll go there. And in DDR2, the data speed rate is increased. Here we are having 266 to 400 mega transfer per second, but here we are considering it upgraded to 533 to 800 mega transfer per second and 4N prefetch. And here also bank is also increased because of the more storage purpose. And coming to the DDR3, DDR3 transfers 800 to 1600 mega transfer per second, means here we are using the around frequency 3200 up to 3200, but in DDR4 where we used that around 1200. I didn't know that value clearly, but around 900, yeah, 32,000 megahertz, 34,800, some around that figure. We used that much frequency. So coming to the DDR4, DDR4 only main impactable thing in industry. DDR4 they introduce bank group concepts. Means parallel accessing concept is occurred in the DDR4, and also prefetch is 8 and prefetch we are introduced in DDR4. And coming to 5, 5 is they are using 16 and prefetch, and frequency speed is more, and also they are going to be planned also more number of bank groups to increase to access the data independently. So these are the comparison. See how much mega, yeah, see in DDR4 we 3200 mega hedges these mega transfers. So for that we are using 1600. Yeah, as I mentioned, 3400 megahertz for DDR5. See, this released on 2020, and the bandwidth GBs we used generally 38 GB per second. So this is the DRAM top view. Means what are the signals we have? We have act and signal is nothing but the activation command, and the these A16, A15, A14. These are the two signals. Depends on the one control signal we have to take internally. Based on that control signal, whether it is a high, we need to select these address bits, or else we need to select these control bits. So RAS, CAS, write enable or read enable. Uh, and these we have main in DDR we have 16 address lines, and four bank groups and four banks, and chip selector. These CKT and CKC are the these two are the uh, what I need to mention is here invertible signals, and DQSTR also. DQ is the 64 bit. This is the main data bus we used. Only it support up to 64 bit only. From 5 layer to DRAM layer, data bus should be using 64 bit only. And this is the strobe bit. And as we know, chip select and reset are the global signals generally we are having. And this is the internal what are the signal, what it done, what are the things, what are the functions of the signals. And coming to the wrapper, see right now I talked row address, column address, bank, chip select, rank, these all are things. How it integrated internally. See here. For example, this is one block. See this block. How see this block, for example, we are having this is our bank groups. See here, bank group. In one bank group we have four banks. So for that, these bank groups we have four bank groups individually, and each bank group we have four banks internally. And for every bank group we have some one sense amplifier. uh, for every banks we have one sense amplifier. One for all these four banks we have only one shared buffer. So for that purpose only, mainly they consider the coming to the bank groups, it comes into the picture. IO gates or DM gates, all are the things. After this row address selection and column address selection, it goes into the bank groups. Control address slash column. See here. Uh, right now, those all are the basics. Okay, this is the main thing. We are going internally depth. If you have any doubts, please let me know, because this is the good opportunity. No one will tell you this much DDR information, working information to you. So, hope you have any doubts, please let me know whenever we are discussing. Okay, see here, and this is our memory organization. This is nothing but one DDR chip. This is nothing but the memory, DDR memory chip. See, for these memory chip, these all are the DDR blocks. This is one DDR. We are having DRAM chips. These all these blacks are DRAM chips. And using channel is nothing but the it is a physical port. While TEB explanation will get into the channel comes into the this DIM is generally we used R DIMs. DIM is nothing but the dual in memory module. Means both sides we are considering the usage of the memory modules. And coming to the using after DIMs, we need to select the ranks. Here rank 0, rank 1 we are using in this chip. Actually we used quad rank, and using ranks, using chip selector we select the rank, whether we need to use a rank 1 or rank 0. After rank selection, using chip, we need to select the chip, which chip I need to perform the operation using which chip. After chip, we need to select the bank group. in chips we have 4 bank groups. After bank group selection, we need to select the bank. For which bank we need to be do the operation. After that, we need to select the row. After row, we need to select the column. I think you get an idea between the row address selection and column address selection. How it should be selected. After selection of the column, then we'll get that particular block memory with particular address where we need to write the data or when we need to retrieve the data. So these are the main organizations, so main things. What are the DRAM operation for to write that internally? We never notice all these things. Internally only all these things are done. See here, channel, what I mentioned. Channel is nothing but the physical port between memory and the memory controller. See, DDR is a one memory controller. One memory controller means what actually? Wait, get clarity. CTB architecture. For seeing that, we'll get clarity. See, for example, here, this is our DRAM. This is our DDR controller. So, what the thing we have to do is here, DDR subsystem, here we have. This is one user. This is DRAM. DRAM is nothing but the memory storage purpose we are using. Whether our DDR is, we are verifying this DDR subsystem. Means what I need to convey is using this memory, just using this memory, whether our DDR is working fine or not. So we are not verifying DRAM, just we are verifying DDR. Means what I need to mention is already DRAM. So DDR is nothing but the operation whether to write or read. So for writing or reading, we need some block. So DRAM block we buy from so and so vendors. So whether right now our DDR is working correct or not for that purpose. For example, in our real life, we want to match it. For example, you need to learn Scooty. But initially you are not buying scooty, you are taking it rent. So but the main thing is need to learn the driving of scooty. So the same thing we are mapping here, we need to verify our DDR. So DDR verification is either to writing or reading the operation with memories. So we are buying DRAM when not buying, we are like that only. We are taking some up to particular months we need that vendor DRAM vendor agreements for that, and we are taking that DRAM. So I think you got my point. We need to verify our DDR, not verifying DRAM. Using DRAM we are verifying our DDR subsystem, the main thing. So by the way, from DDR to DRAM, we are having some other layers. This is the physical layer. DDR5 means nothing but physical layer. Channel is nothing but here only. See here, we are having 2 lines. This is nothing but the example. We have some number of DRAMs. One DRAM here, another DRAM, another QSPF DRAMs here. So for the selection of these DRAMs, selection of other memories, we are using this channel. Channel is nothing but the physical port for selection of the memories, like that. The physical port between memory and memory controller. Memory controller is nothing but the DDR controller. DDR controller we need to call like the memory controller. So memory controller can also access individual ranks at a time, individual ranks of RAM at a time, we are having multiple ranks, dual rank, quad rank, octa rank also, and dual channels also we need to have for selectioning of RAM 1 and selectioning of RAM 2, parallel things should be occurred. So parallel both channels we need to select, and dual channel provides highest performance also. By the way, improving our channels will have the more throughput to improving our maintenance and improving our data transfer fast. And coming to the DIMMs, DIMM is nothing but the dual in memories. But here we are using DIMMs. But initially DDR1 and SDRAM they used SIMs. SIM means nothing but the single inline memory module only. See, this is the only one side they are using. After that, for system, it required only 64-bit of data to the motherboard. Only, for example, we need two SIMs. Means, for example, we need to transfer data 128-bit of data. So we need to put it two SIMs. So instead of using these two SIMs, these DIMMs is comes into the picture. Then for 128-bit of data connection, so one DIMM is enough. So one side we are considering 64-bit of data, another side we are considering the 64-bit of data, and it provides the ranks on both sides. Yeah, SIM is nothing but the providing, DIMM is nothing but the providing ranks. Using, as I mentioned, chip select is mainly used to select the specific rank, which rank. For example, in this DIMM only we are having rank 0 and rank 1. So which rank we need to select, according to that only chip select should be, chip select signal should use them. See, we are going internally one by one block, channel, DIMM, SIM, rank. So if you have any doubts, just please let me know. And coming to the ranks, see, this type of memory organization should be occurred in DRAM. See, all these are the memory arrays. See, rank 0, rank 0, rank 1. See, one, as I mentioned, DIMM rank 0 and DIMM rank 1. See, using chip select, I used this rank. So, either chip 0, chip 1, chip 2, chip 3, depends on this chip. So, after selection of rank 0, there will be another 4 options to go to which chip. So after selection of the rank, after selection of the chip, see internal architecture of the RAM. See, after ranks we have different banks: bank 0, bank 1, bank 2, bank 3, different banks. Then see, we'll complete this rank option. Yeah, different ranks we have: single rank, dual rank, quad rank, octa rank. For example, quad rank is nothing but the 4 ranks we have. Like this, like for example, rank 0, rank 1, rank 2, rank 3. After that, we need octa rank, means we need to take two chips at a time of quad ranks. Then it comes under the octa rank. See, after selection, how rank selection should occur? See here, rank 0 and rank 1. So CSN not bit is selecting to the rank 0, and CSN1 bit is selecting to the rank 1. So for example, what are the address or data? Address is selecting rank 0, data is selecting rank 1. Or else address of 0 to 32 is selecting rank 0, data of 0 to 31 is selecting rank 0. So these all these comes under the configuration. How we configured, they at that type only internally they will select. And coming to the width cascading, see here DQ you're having DQ0 to DQ7. So cross 8 DRAMs we are having in ASIC, for example. And also width cascading, we have mainly cross 4, cross 8, and cross 16 DRAMs also. These are the DRAM different types. I will give you some clarity while going into that. See here, DQ0 to DQ3, only 4 bits only allow for if we use cross 4 DRAM. Only 4 bits we are using in cross 4 DRAM. But we are using cross 8 DRAM at a time 0 to 8 bits they are accessing. So if we use cross 16 0 to 15 at a time, this DRAM will access. So for this, what the thing main thing is, parallelism is improving. Whether we didn't want to select the channel rank 0, channel dim rank, chip select, bank group, all the things are again don't want to select all the things here also. So for this that throughput is improving. And coming to the bank groups, why bank groups came into picture? Even banks we have. After ranks, we are having bank groups. So bank groups means, for example, see for example, this is one bank, bank 0. The same we are having bank 1 and bank 2 and bank 3. Only 4 banks will have in DDR3. Means in DDR3 we don't have bank group concept. So here the data, so here 0 to 15 for example, we are selecting one row, seventh row we are selecting. So after selecting these, what are the data present in the seventh? These should be shared into this buffer. After that, we after 7 is stored. We don't want to select after I need a ninth also. So after 7 stored into the IO buffer, again this IO buffer is shared into the shared IO buffer. So after seventh row shared IO buffer is stored into the this shared IO buffer, then only we'll select this ninth buffer. Please wait for 1 minute. I am getting one call. Yeah, sorry for the interrupt. See here, after this 7 data, it comes into the shared IO buffer. After that, we need to select a ninth. So these type of here, what the main thing is, waiting is done here. So to avoid all those things, bank groups comes into the picture. Means for bank group, every bank should access them parallelly. After these IO buffer is filled, then we need to access this bank. So those type of things didn't take time. So main thing is to access the 2 banks at a time. For example, after bank group, we are having individual buffers. So 4 banks, 4 buffers, 4 IO buffers we are having. So I need to select bank row 3 in bank 3 and row 9 in bank 9. So the row selection of row 9 is select and it's sent into the bank 1 IO buffer. Then row 3 selecting into the bank 2 IO buffer. Then the data which is present, those things is shared into the shared IO buffers. These are the bank groups internally should occur. See here, bank selection. After that, after selection of the bank group, which bank we need to perform the operation. That is nothing but the bank operation, bank selections. See in banks, what we have mainly in banks we have memory array, row decoder, column decoder, and the sense amplifier. See, I already mentioned that how the row decoder should occur. After row decoder, how we need to select the memory array. After that, column decoder should occur. After column decoder, where the data should be done. These coming to the cross 4 and cross 8 devices. I will give right now. If I explain you, actually this is an confusional concept, DDR. So it won't possible to get clarity within 2 weeks. So you need to work on it. Then only you'll get the more clarity. If you have any idea, basic idea, all the things, then you'll find. Otherwise, you didn't get any clarity. So it will be a very dry concept, either to learn or either to work. It is more, we need to take more conscious whether to understand all the things. We need to work with more responsibility, only we'll get the things by the end of the day. And this is the DRAM sizing and the addressing. As I mentioned, see here, I mentioned DRAMs. We have different DRAMs. That is, one is cross 4 DRAM, cross 8 DRAM, and the cross 16 DRAM. So, cross 4 DRAM, we have only 4 data pins. And cross 8, we have 8 data pins. And cross 16, we have 16 data pins. So, depends on the size and the row address, lines are changed. Yeah, this is nothing but the 4 GB data, 8 GB data, and 16 GB data. How the calculation should be occur, I will let you know. And the column row address is dip vary. For example, uh, actually in DRAM we are having A0 to A16 address lines, but depends on the these cross 4, cross 8, cross 6 configuration. Row address is always varying, but column address is always constant. A0 to A9, total 10 column bits we have. But coming to the row address bits, depends on these configurations only. We'll get the whether A0 to A14 or A0 to A16. Based on that, we'll have DRAM may available 2 GB, 4 GB, 8 GB, 16 GB. Depends on the ZB configurations. These calculations you know. And coming to the prefetch architecture, as I mentioned that what the thing is, prefetch architecture is the main thing which have the parallelism concept and more throughput. Previously, DDR1 we have having only 2n prefetch. Right now we are having 16n prefetch also. That is fine. What is prefetch means nothing but, as I mentioned that row decoder, column decoder, I selection after bank selection we are selecting that row and column decoder. Na? After row decoder, we are taking that entire row into the sense amplifier. Why? We just want to take that after selection of that particular column, then we should take now. Why the particular total row they are taking? So here only the main prefetch architecture concept what the think and they designed is the total particular row they are taking. So column bits have 10 bits only, A0 to A9. So for example, I am selecting seventh column. So in DDR2, internally after 2n prefetch means both 7 and 8 they are taken, and they will give into the 7 will give into the output, and 8 is 8, and 2n means 7 8. So 4n means 7 8 9 10. So sequential data, what are the data beside after selecting that particular column, the consequent values 4 and 8 and based on the internally they will take the whole data and they stored into the IO buffers. Some buffers we have, and they store into the IO buffer. And after that selection, again I am what I after that seventh data I taken, again I am requesting for the 8 data. So again they didn't select that rank, chip, sorry, dim, bank, group, bank, row, though those they didn't need. First they will check, after that they will check IO buffer whether we are having that 8 data. Yeah, 8 data we are having. So they will give that 8th data. After 9th data I am asking. or else I am asking the group data. After 8 to length, I will give an ax length. I will give some length data. Length 3 I given. So 3 plus 1 4. So 8 to 4 12 up to 12. The data should be given in the burst type they will give. So this is the main prefetch architecture they develop. I think you got the prefetch architecture concepts. And coming to the command truth table, we'll have one minute. Yeah, up to clarity. Yeah, hello, please anyone up to now you'll get clarity only. I will move on to the other topic, or else it is a waste of time for you and me. Hello? Yeah, anyone please, Srikanth, Mohammed.
Actually, this involves memory concepts, right? So people who are aware of memories, for them, I think it is understandable, but for others, it might be little complex.
Yeah, actually, I mentioned that here is the most confusion thing. One day you didn't understand all the things, but either you have brief idea or not about the banks, what channels, at least the terminology.
Mm, at least means
At,
my MTech thesis was on in-memory computing, so I know, but for others, I'm
yeah,
not
yeah,
sure whether.
yeah, yeah, yeah. Okay. From your side, you will get you have idea. Actually, you have all these memory concepts. Yeah, and anyone from others, Kavya, Amit, Bindu, Muhammad, Shalimar, Vansha, some other people is also Jivita, Shashi,
That
Ronald.
are fine, madam.
Okay, okay. And any more else? If you're stuck in any concept, I will explain it once again. Yeah, Kavya, do you have any queries from your side?
No, ma'am.
Yeah, okay, okay. Anyone is there? Bindu, because this is the not any guest lecture. I don't want to do like that. Whether I don't need any feedback from your side. I don't know whether you are getting the points or not. Actually, it is. I mentioned that it is very difficult to understand in one day or 2 days. But at least you'll get some idea now, or else it is waste of. Yeah, okay, fine. Can I continue?
Yes, ma'am.
Yeah, okay. Thank you, Amit. Amit, do you have any queries, or is it clear?
No, ma'am. Is it clear?
Yeah,
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 ma'am.
okay. Yeah, okay, okay, okay. Thank you, Amit. Mm, See here, this is the DRAM subsystem. What the DRAM subsystem is. Uh, Wait, I will explain my TB architecture. Wait. Just a minute. Hmm. Hope my screen is sharing. See here, I'm just giving you an overview. Actually, I don't want to share. Hello, hello.
Yes, ma'am.
Yeah,
Yes.
yeah, yeah. Actually, I am explaining my TB architecture. See here how it should occur. See, this is my TB architecture as what I developed. This is a DRAM. This is the memory controller. Uh, in memory controller, we are having controller block 1 block and the 5 block. We are having blocks. One is the controller block and another one is the 5 block. This is nothing but the DDR subsystem also. DDR subsystem. We are verifying this DDR subsystem using DRAM. This is our RAM, DRAM. So here we are using two agents. That is one is a APB agent, another one is AXA agent. APB agent and another one is agent. See, we are internally we didn't go these blocks. Later we'll go. Here these APB using we are using mainly for the configurations. So what are the registers present in these controller and the file? Those registers we are configuring using the APB agent. And using AXA agent, what the thing is, we need to initiate the traffic to the controller and the file. See here we are having AXA slave agent, AXA slave, and here we are having AXA master agent, and here we are having a APB slave agent, and here we are having. I am not drawing it clearly, but I am explaining. Make sure that you should have clarity. And here I am having APB master agent, and using APB, what are the registers present in the controller block and the 5 block? Those registers we are configuring using APB, and using AX agent, we are just initiating the traffic to the our DDR subsystem. So generally, AXA initiating traffic means all the signals like AW address, AW data, AW burst, and either AR address, AR data, AR size, AR length, AR uh, some other signals like a catchy, priot, buffer, prot, all the things. Those all are the signals we are having in the right now we are having in the controller block. In controller, we have some other blocks that is nothing but arbitrations and some other um, priority based things, ECCs, buffers, write buffers, read buffers, merge logic, and command schedulers, all the things we are having controller block. And coming to the phi is nothing but the physical layer. So what the controller block will mainly do is this is the our logical data. So these logical data is converting into the physical data. Generally, see, and one more example I am taking here. Here all DRAM signals are like how row address, column address, bank group, bank, all the things. So, but we are initiating the signals like AX data, AW data, AR data, but they didn't want to communicate them, so that these data logical data should be converted into the physical address data. Those data should be converting into using controller block. I think you will get the clarity. So like for example, These, for example, AXA is known only one language, that is nothing but Telugu language. And DDR don't know that Telugu language. DDR know only English language. But here one Hindi people is available who knows both language. So these the people who are known both language, those language should be converted here into the data communication should be passing into the DRAM. I think you'll get some clarity. So these logical data is converted into the physical data using controller. So while conversion, we need to make sure that we need to follow the some timing rules. So those timing issues should be clarified. Should take care of all the things should be by 5 block. So in 5, we are having some PLL timing issues, DLL timing issues, phase locked loop, and differential clocks we are having already, CKT and CKC. Those things, all the timing related things, all the timing controllers things should take care of the 5 block. Then after 5, it will select using channel, it will select the RAM and memory. After memory selection, using memories, in memory we are having different DIMMs. Then we'll select the DIMM. After DIMM, using, for example, if you are using 2 DIMMs, using any control signal we'll use. For 0 we need to select that DIMM, for 1 we need to select this DIMM. After selection of DIMM, we are having 2 ranks, rank 0 and rank 1. Using chip selector, we need to select that particular rank. In after particular rank, we are having some different chips. So for example, as I mentioned that cross 4, cross 8, cross 16. So DQ pin is nothing but 0 to 64 bits. So for cross 4, we are having 4 chips. 4 chips. 8 4s are 8 8s are 64s. So 8 4 16 30 to 64. So every chip we are having 16 bits of data. So 16 16 30 to 16 again 16. Total 64 bits of data. So after rank selection, we need to based on the configurations, cross 4, cross 8, cross 6 configurations. Based on that, we are having chips, number of chips. For cross 4, we are having 4 chip. Cross 8, we are having, so uh, cross 16, we are having some number of chips. So according to that, we'll select that particular chip. So that is comes under DRAM addressing calculations, as previously I skipped. I will explain it after completion this explanation, then you'll get clarity. After this chip selection, we need to select that particular bank group. See here, conversion controller only will give all these. For example, we have some second bank group. In second bank group, we need to go to the third bank. After third bank, we need to go to some 65th row. After 65th row, we need to go to the 73 column. Like that, those physical data conversion should be occurred by the controller only. So we need to verify the controller. So the main task is to the conversion the AXA data into the DDR data. That is nothing but the logical address into the physical address. After bank group selection, again we need to select the particular bank. After bank selection, we need to select that particular row address using row decoders. Then after row data comes into the sense amplifier, we need to, after some particular TRCD delay, after we need to select that column, then we need to do either we need to do write operation or read operation. These are the TB architecture we need to do like this. Generally, either DDR 3, 4, 5, 6, anything. I think you'll get the understanding of this TB architecture, or can I explain it one more time? Can anyone? Because this is the one thing, main question you'll get whether you are attending the interview. Of after seeing the shortlisted resume, then if you mention that I have an idea, I have worked on, I have good knowledge on DDR, then the first my question from my side is, can you please explain the your TB architecture? Like that, so you need to explain all the things, not all this internally. You have to mention that this is my TP architecture. In my TP architecture, I am having two agents, APP agent and AXA agent. APP agent is mainly to configure the registers of the controller block and 5 block, what are the registers, and AXA is mainly used to initiate the traffic. Then controller will have that conversion of logic data into the physical data, and other some arbitrations and command schedulers. All the things are done by the controller block. In some timing issue calculation, timing correction things. After that, the date particular row. Then after, I forgot to tell you here that here we are having scoreboard. After the data written to the particular row, again the address coming back into the file. After coming into the controller, again the data conversion decoding is happened, and here we are having one monitor. Then 1 minute, 1 minute. Sorry for the interrupt. Hello. Yeah, sorry for the interrupt. Yeah, where is we start here? Yeah, the data. See here. What are the data present in that DRAM where we've written again coming into the 5 block. After 5 block, it come into the controller. Then controller will change that physical data into the logical data. Here we are having AXA monitor. Then we need to take all the taking all the signals from our DUT. Then DUT is nothing but here DRAM only. Then monitor main work is capturing the signals from the DUT. So we are taking the signals from a monitor. Then here we are having one scoreboard. So here scoreboard, actually that golden reference is taken by the AXA. Then the monitor signals is taken. Then whether the both the signals is having the same um, comparison should occur here. Both the signals are same. Then our test case is passed. Otherwise, we'll get an error. Then we'll debug it. Which type of error type depends on those errors. We have to debug. That is the TB architecture and what are the things we need to mention. Whether they ask, the question is might be like how you verified, how you verified in the scoreboard, how the signals is happening, how controller will convert all these things, how time, what was the work of the 5 block, and in DRAM which type of ranks you are used, and using rank selection which type of signal you are using dim with which type of signal you use to select that particular dim, and which bank group, both the bank groups work similarly. So these questions mainly they focused. So I think I overview all these questions. I answered the overview answers for all these questions. And one more concept up to now, you are clear. Depends on the memories and all the TB architecture. Then we'll depth into that. Previously skipped one command scheduler, DRAM addressings. See here. This is the DRAM addressing. See here. As DRAM is in different size, either 2 GB, 4 GB, 8 GB, 16 GB. But our DQ is in 64 bit. Remember this one. Our DQ bit is 64 bit. This is constant, 0 to 64 bit. So based on this bit of this bus, DQ bus, depends on the configurations. How many chips we are having, how many DRAM chips we are using. So for that, see here 4 GB data and cross for configuration. How many banks, how many rows we are having, how many columns, and also one more thing is page size. Page size is nothing but the total data. Actually, memory sizes is measured in pages. So for that, we are using this page size. See here, we are having 512 megabits and using cross 4 configuration, cross 8 configuration, and cross 16 configuration. Our 2 GB address data DRAM size is 2 GB. But configuration cross 4 is different, cross 8 is different, cross 16 is different. So cross 4 configuration, bank groups having 4 bank groups, and four bank groups for cross 4 and cross 8. Bank groups have 4, but only for cross 16 we are using only 2 bank groups. The reason behind is some design specification issues like that. I'm not sure. And coming to the bank address and bank group. Bank address and bank groups are mainly bank groups are 4. So zero bank group 0 to bank group 1 means 00011011. So for 4 bank groups we need 2 bits. So bank group address. For cross 4 the same, cross 8 and cross 16 is also same. See here cross 16 we are using only 1 bit because we are having only 2 bank groups. So 1 bit is enough to select the 2 bank groups. So coming to the this row address and column address, row address apart, column address. See here, column address is always constant. A0 to A9, 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 A0 to A9. The same thing, all the things. Column address is always constant, whether it comes cross for configuration, cross 8, cross 16, either it 2 GB, 4 GB, 8 GB, or 16 GB. And the main thing is row address selection is the main thing. See here, how it will select. See, here A0 to A14, A0 to A13, A0 to A13, and A0 to A15, A0 to A16, A0 to A17. These the things. How the row address selection should happen. See here. How means we are having 512 MB here. 512 MB. So 2 power 9, 2 power megabit giga 29 minus, we need to remove that the GB 2 power 2 here. So 2 power 27. After that we have to remove the bank group. So 2 power 2 again. So 4 bank groups. So 2 power 25. 2 power 25. And for 2 power 25, in this 2 power 25, we need to select that uh, first we need to divide that column width because of a constant. So in 25 lines, we are using 10 lines per column. So again 15 lines is there. So 15 lines is there. So those A0 to A14 we are using as a row address line. Only for 512 MB cross 2 GB data and cross for configuration. So the same 256 MB cross-site configuration, 2 GB addressing. So these address calculations is the vary from one thing to another thing, 1 GB to another GB, and one configuration to another configuration. Mainly row address only, and remaining all are the same. And coming to the page size calculation, as I mentioned that page size is nothing but the storage of the total. For example, memories should be showed in the pages. So here 512 byte, how will you get? Actually, page size is calculated in the bytes only. So total number of rows into configuration. How the configuration, either is a cross 4, cross 8, or cross 16, depends. And again it converted into the bytes. Then we'll get the page size, either 1 GB, 2 GB, 3 GB, 1 KB, like that. Depends on the our configurations. Actually, I just give the basic idea only related these DRAM, how we can get all the things. Yeah, prefetch architecture is done, DRAM size calculations is done. This command row table, yeah, command. We'll get the will complete. Yeah, the architecture. See here, as I mentioned, the processor AXA transaction is initiated, and here this is the controller block. We are having the address and arbiter command block, and DBM block, ECC block, and time management block. In Pi block, we are having PLL, DLL, address initiation, calibrations, and the time and calibration things are mainly done in the Pi block. Then using interface, we are transmitting. See here what the internal blocks is working is nothing but the address and orbiterator. Orbiterator is nothing but the priority, which command I need to do, which thing I need to bypass it right now, or which command I need to pass it right now. The arbiterations, priority based, and the command block, which command scheduler thing is the main thing, and ECC error correction, and DBM. Actually, I don't know that. Okay, bus management only. Um, Actually, I worked on the arbitration block. I have an idea, hands-on, and timing management is also okay, fine. And we have to maintain some time management after activation command. Minimum 2 cycles require TRCD delay. After that, we need to give the column command. After column, then immediately only we'll get the data, or we need to write the data. And coming to the Pi block, actually Pi is also in our project. What we done is controller only we verified mainly. In Pi we are not verified. Generally, as of my knowledge, in we have to verify only one block. Already verified pies only we have to take in here actually. So at a time, both IP verification is not possible. So one verified IP we have taken, and we verified controller block. Our duty is there. That is thing. And data mask, data bus, data signals, DQ bus. DQ bits are, as I mentioned, 0 to 64 bit. So those bits are masked because they don't want to see whether the data, which type of data we want to write. So the data should be masked, and data should be which data bits are, which data bytes are valid. And the coming to error correction, if we get any errors, how can we write based on the timings only will have. And the major concepts I need to cover so many things, that power up initializations, these ZQ calibrations, and the write training, retraining, and these commands, and the parameters. These are the main timing parameters we need to cover. Then only you'll get some clarity. Otherwise, uh, these are the mode registers. Okay, up to now, if you have any doubts, please let me know. Then only we'll go to the next concept. Yeah, yeah. Do you have any doubts up to right now? Hello, hello, hello. Can anyone please confirm? Do you have any doubts, any queries?
No, madam.
Okay, can I continue?
Yes, madam.
Yes, ma'am.
Yeah, okay. Thank you. We'll go for one more concept. Yeah, this one is on this command truth table. See here. We are having, sorry, we forgot that DRAM commands here. Yeah, after that we'll go that command truth table. See here, we are having different signals. What the signals is done here. See. This reset is the global signal. Generally, everywhere we are using active low only. Whenever the signal is high only, it comes under, whenever the our reset is high, then remaining all the signals comes to the reset condition. All the things should be in the zero state, like that. Then coming to the CSN, this is an chip which in particular GB DRAM, which chip we need to select. Those the things. After that, these CKE, clock enable signal, and this clock, based on the clock only everything should be occur. So these clock signals only depends on the whether it is high or low. Then clock, after clock in comment truth table we'll get some clarity. Then in CKE high only, then the remaining these differential clocks CKT and CKC should be comes into the picture. And CKT and CKC are the two differential clocks. Means see, generally we are having one clock. Generally we are having this clock like this, no? This is CKC clock and this is CKT clock. So nothing but the differential signals. You'll get you get my point. And coming to the DQS and DQS signal. See, this is nothing but the data bus. And the data bus strobe. These the data bus and data bus strobe are the 64-bit of the data. Means how data written should be for writing the data or reading the data. This bus only we are using. And coming to the these are two enable signals are RAS, CAS, write enable A16, A15 or A14 based on the command truth table, whether we need to select address bits or the these RAS, CAS, WN bits. Depends on that ACT and the CSN. If our ACT signal and the CS are low, then row address bit, then these are the interrupt as the row address bits. Whenever the ACT is high, then are the then it comes into the read of write or other commands. See, whenever our activation command and the CSN command are low, then we'll select these address bits. Whenever our activation command is high, then we'll select this row address bits. Whenever activation command is high, it is pointing to the RAS, CAS and write enable. Whenever act high and CSN both are low, means deactive, then we'll select address bits. That is the thing. And active command and bank groups, banks, 2 bits we are using, and the address A0 to A13. See, this is the things. DDR wrapper, DDR memory interface, memory array, control logic, refresh counter, row address decoder, column address decoder, all the things as we are. We'll see this command root table. As I mentioned here right now. See, CKE. CKE and CKC and CKT. Both are the differential signal. Comes under the CKE clock only. We are having different functions, commands. See, first we are seeing mod resistor set. That is MRS commands. So both CKET and CKC should be high. Then our CS command should be low. Then ACT command should be high. Then RAS should be low, and the remaining all should be low. And bank group and bank activated. Then remaining are okay. For the main thing I need to mention, for bank activation, for example, if you want to do bank activation, so for that we have to use act command. This is the main command for everything. Initially after boot up process we need to use act command. For act command, the main thing is our CKE should be high and CSN should be low. CSN and after CKE high only, then we'll select that remaining all the things. Our CSN low and ACT and low. Then these three act as the row address bits. See, right now I give explained. See, both the CSN low and ACT low. Then only row address bit should be ACT. These three bits act as the row address. Means A16, A15, A14 are working. Then we are selecting bank group, bank address. Then C2 column address, and remaining, see here, A12, A17, A13, A11, A10, A0 to A9, all these comes under the row address only. These are also 2 bits. this is A12 or BC. This is a burst stop. BC is nothing but burst stop. Based on the bytes, based on the burst, we are using this signal. And A17, A13, A11 are the address signals only, and A10 and AP. AP is nothing but the auto precharger. And here the main thing is precharge should be occur. I will explain while going to the timing diagrams. Auto precharge means every time we we never want to precharge. After completion of one command, again it comes to the auto precharge. And A0 to A9 are the address signals. The main command should know is bank activation. So for bank activation, our ACT and the CSN both should be low. Then only all the remaining bits act as the row address bits. And coming to the, for example, we need to write something. Uh, we need to write without auto precharge. See, we need to write. So for that, clock should be high. Then our ACT and command is high, and CSN command is low. Then I am selecting here row address because ACT 10 is high here, so it both are different here. Means both one is high and one is low, so they are not selecting these row address bits. So for that they are selecting row address strobe only, and they are loading these row column address strobe and write enable, and selecting bank and bank group, and here using auto precharge high because I am writing with auto precharge. So for that this command should be high. So these are the what the things is we have to know which signal is high, which signal is low for to perform these function. The main thing is, for example, we have to perform read with auto precharge. So for reading, CS signal should low and ACT signal high. Then RAS is high and CS is low, and write enable is high, bank address, bank group, and auto precharge is high. So all the things according to the JDEC spec, we need to configure it. Means nothing but we need to configure our registers, every registers. See, for example, read with auto precharge. We need to configure all the things using the coding. Then, for example, we are writing test cases with read with auto precharge. So, according to on that particular sequence, we need to import that sequence, and we need to run that particular sequence. And before running the sequence, we need to configure all the registers using APB and using with these command root table. Then only our test case will pass. So the same thing here. And meanwhile, I will explain this self entry, self refresh. Entry, self refresh, exit. A refresh is nothing but after reaching to the particular command, particular threshold voltage, refresh command should be occur. And coming to self refresh entry, self refresh exit, and this is a power down entry, power down exit. All these comes under boot up process. After particular, see for example, we are starting our laptop. So at the time of owning our power button, initially it is setting up all the things. It immediately not opening our window table, like our wallpaper. It is not opening. Initially, it is setting up. That is nothing but the booting time. So at that time, some resistors are completely off mode. So again, it is initiating it to them, and again it coming. It is coming to the on process. So those the things should comes under the boot up process. And some power down conditions. For example, I am keeping my laptop like that. After some particular timeout it reached, according to the designer, after some particular 1 second or 1 minute or 2 minutes, again it goes into the sleep mode internally. So at that time, some resistors, some configuration resistors like display board resistors and the lights which is using in the keyboards, those related configuration registers are configured as after it reach into the sleep mode. So these are the things should be off like that. So those at the time some registers is power down mode, sleep mode. So again it comes in at the time the registers are in sleep mode, they are not working. So again we are using our laptop, we are just touching it, again it coming in. So for that we are saving our power, we are saving our battery lifetime. So without using we are wasting our battery. So initially these are the internal things setups should be done. The same way for DDR also. We are not using the DDR block, but it is still in wake up state. So it is the waste of the power. And the by the way, is wasting means it is continuously working means it comes under some complex issues and the system downfalls and the some fallback issues should be occur. So those the things to protect. These are the many features they are added. And coming to the so no operation mode means see here we are not doing any operation, then it no operation mode is activated automatically without using these things. Read with auto precharge, burst shop. See here burst of 4 on the fly. So at the time CSN bit is low, activity is high, and RAS bit is high, CAS bit is low, write enable is high. Bank group bank address selected, and see here BSN BC boss shop N is low here. Why I am selecting BC4 for the same BL8, the same bit is high here because boss shop for BL8 it is high actually, for BC4 it is low. So according to the JDEX, how this is the spec definition. So according to that, see here BL8 on the fly, BL8 on, BC4 off, BL8 or BC4 fixed. So not chopping here. So like that is also there are so many variations. And coming to the ZQ calibration is the main thing. We discussed it later. In a fresh mind only we'll get this clarity. See memory access. How can we access the memory sequentially, continuously? Bank 0, bank 1, bank 2, bank 3, bank 4. All the memories will going to the bank 1. After writing a completion of the bank 1, we'll go to bank 2. Or else we have to write the interleaved also. Bank 0 we started. After writing first row, again we are interleaving to the bank 1. Bank 1 zeroth row. After bank 2, first row we are starting. Meanwhile, bank 0 other bits we are writing. So the interleaved access is also uh, one of the best feature in this DDR. That is the thing. Yeah. Yeah, actually it is our first class. Do you have any queries? Okay, please let me know. We have 10 more minutes. Can you actually want to start it initially, but right now I'm starting. Okay, can you please introduce yourself and how the session is happened? What are the things you are expecting more? Is any more improve things from my side? Improve is not your suggestion. What the things you want like that? Okay. Can you please one by one you can start? Yeah, we'll start with Shrikant. Right now you are working in any company?
Yes, actually, I'm working at ARM, but
Okay, Shrikant.
it's just for the refresher and all. I thought of enrolling for projects.
Yeah, okay, fine. Right now you are working in which project?
Currently, I'm working means I'm in the part of emulation team, and currently I'm working on Ethernet.
Acha, okay, fine. Maybe DDR and Ethernet both are some
They're totally different, but yeah, I have worked on HBM before, so
sorry.
it's they are little different, but I had worked on HBM
Yeah,
before.
HBM.
So uh, with that basics, I can map and means for anything means whenever we are reading any memory related protocols, JTAG specifications are must until and unless you do
Yes.
specifications, it will be difficult.
Yeah, Shrikant.
And having some memory knowledge is helpful, like how read write
Yeah,
happens, basic cell structure of 60, then DRAM based on capacitor charge, how it store the bits. That is basic, but then rows and
that.
columns, row decoder, column decoders.
Yeah, those all are the basic, but coming to who have this memory idea only, they will know. Depends on their project.
Yes, means coming to this session, I think it was good session only, but this topic itself is little bit
Dry topics.
yes. So in just means just by listening, I think for everybody it will be difficult. So I think uh, all of us should just get back and try to get some memory basics, read some specifications, and maybe read this lecture means listen this lecture again, and maybe it will be better for everybody.
Yeah. Actually, before you have to uh, attend the session, minimum you need have some memory basics. Then only you will want to map those things to what I want to not teach you. I want to guide you.
Yes, yes,
So
yes.
then only you'll get because these are the memory related projects. So without the memory basic knowledge, we don't want to. Even what I guided you, what I transferred my knowledge, you didn't catch the exact point, my intention. If you have just basic idea, then you'll got my point. Okay, thank you, Shrikant.
Yes,
And
yes.
yeah, okay. If anything you want, just uh,
Yeah,
me.
sure.
Yeah, okay. Thank you, Shrikant. Coming to Kavya.
Yes, ma'am.
Uh, yeah. Do you have any queries from your side right now? You are working or?
I'm studying engineering final year, ma'am.
Acha, okay, fine. Actually, it is very good, but it is very difficult to map you, even though, yeah, Kavya. Do you have any queries? Okay, do one thing. So right now you are starting your career, and one advice from my side, you just want to read all the memory concept related things. Then you just map all these things. Then only you'll get some idea.
Yes,
So
ma'am.
otherwise, you just want to read that JDEX spec. Okay,
Okay,
thank
ma'am.
you, Kavya.
Okay, ma'am.
Ah,
Thank you, ma'am.
yeah, okay. Mohammed, uh, hello, Mohammed, are you
Yes,
there?
yes, madam. Yes,
Yeah,
madam.
yeah. Mohammed, do you have any queries? Right, you are working?
No, madam. At present, I'm not working. Previously, I worked in Cognizant. I did
Acha,
my
okay.
MS. I have my MS degree in VLSI CAD. Afterwards,
Acha,
I worked in Cognizant. Now there is VLSI boom, so I want to switch you back to VLSI field.
okay. All the best for your
Thank you,
decision.
madam.
Firstly,
Thank
you
you,
are
madam.
already stepped into our field, this field.
Yes, madam.
Okay. You never want to regret as I leave that field I came. But initially it is difficult to get in VLSA, but in future we'll see our growth.
Yes, madam. Yes, madam.
Yeah,
First
yeah,
3 years,
you.
I have to get
Mm,
experience for 3 years. Then it will
yeah, that
be
is the
smooth.
main thing. Yeah, initially.
Initial will be steep ladder, then it will be smooth.
Yeah, yes, actually, yes. Okay. And do you have any queries from your side?
No, madam.
Yeah, I think you got the points. Actually, the thing these protocol have will continue some more depth in upcoming sessions.
Okay, madam.
Thank you, Mohammed.
Thank you, madam.
Yeah, coming to Bindu.
Hi. Yes. Hi.
Yeah, hi Bindu.
Yeah,
Do you
I
have
currently don't
any?
have any. No, I don't have any queries.
Yeah, okay, thank you. May I know you are in which domain? I mean, which
I'm in the same.
projects?
Yeah, I
I
used to
mean,
work as an SOC design engineer. Currently, I'm
okay,
on a break, so I took up this course
yeah,
to brush up on the topics.
yeah, okay. Thank you. Do you have any queries? I forgot to ask you.
No, I don't have any queries.
Okay. You are getting my points. If you
Yes, yes.
have, actually, my intention, I want to give my 100%, but the way of whether you are getting my points or not, that's why I'm giving the real time examples. At that point, also, you are catching my points.
Yeah.
Yeah. Okay, Bindu.
Okay. Thank you.
Thank you. And Ronald, do you have any queries from your side? Similar, Shiva Priya, Govind.
No queries, ma'am.
Yeah, okay, sure. Govind.
Yes, madam.
Yeah, do
Yes.
you have any? Yeah, do you have any queries from me?
No, no, madam.
Yeah, you are getting my points.
Yes,
You
madam.
are.
Yes, madam.
Yeah, okay. If you have any queries, please let me know. Yeah, hope everyone will got my points. If you want to take few more sessions, I think they plan to take few more sessions. We'll see. We'll go some more depth in upcoming sessions. So hope everyone enjoyed the session, and I'll winding up this session. Okay, thank you. And by the way, happy weekend. Thank you.
Thank you, madam. Happy
Yeah.
weekend.
Thank you.
Thank you. Yeah, thank you.